So you've found the perfect home. But high mortgage rates have you second guessing. The Churchill Mortgage team says waiting to buy can be a costly mistake. Try their free 15-minute analysis to see the difference between buying now versus waiting for lower rates. Visit churchillmortgage.com to learn a smarter way to build wealth through home ownership. This is a paid advertisement. NMLS ID 1591. NMLSconsumeraccess.org. Equal housing lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Hello once again. Thanks for joining us. This is Space Nuts, where we talk astronomy, space science, recipes, and how to change a tyre. And my name is Andrew Dunkley, your host. And coming up on this episode, we'll be talking about the fastest stars in the galaxy. And apparently it's eye-popping how fast they're going. And a potential solution to space junk that might be a bit more promising than some of the others that we've talked about in the past. And of course, we'll look at some audience questions about Siding Spring Observatory, the Great Attractor, and factors that affected light we're seeing today that no longer exist. And does that make a difference? All that coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me as always is his good self, Professor Fred Watson, astronomer at large, as the emails roll in. Hello, Fred.
Hi, Andrew. Good to see you again. I've got my tile lever, but I'm still looking for the recipe book
Yes.
for this episode.
Yeah, galactic cookies are the order of the day. Now, if you're wondering why Fred looks a bit funny and sounds a bit funny, it's because his Jurassic 2.1 operating system has finally said you can no longer use your computer unless you update your browser, and unfortunately, he can't because of Jurassic 2.0 or whatever system it is. Yes, never mind. But we will carry on. We always find a way around the problems, which we've been having quite a few of in recent times, unfortunately. But that's life. How are you, Fred? By the way, we haven't seen each other for yonks.
Yeah, very well, thank you. I was at an interesting event a couple of days ago in Canberra, which was the launch of something called Einstein First and something else called Quantum Girls. And these are two initiatives that are being put forward to bring science teaching in Australia into the 20th century by recognizing that what really turns kids on is the exciting stuff like relativity and quantum physics, which are not really taught in a big way in schools. They're sort of brushed over a bit.
Yeah.
This program is designed to give kids a hands-on experience of both of these things. Well, these two programs, there are two of them. So I was at the launch of that at the Australian Academy of Science. Dr. David Blair and actually Professor David Blair and Professor Susan Scott leading the charge on those two initiatives. A great way of attracting kids generally into science, but in particular, of course, young women and girls to get them turned on by quantum physics and relativity.
Fantastic. We've got a similar thing happening tomorrow in Dubbo with a Girls in Aviation Day. And lots of astronauts have started their careers in aviation. So that's a big one for us. And it starts at the age of 8, this particular program. So that's going to be great. My eldest granddaughter's not quite old enough, but I reckon if she went, she'd tell everyone how they're doing it. You know, she's not backwards in coming forwards. I remember, I'll tell you this story. We were at school a while ago now, picking her up, and there's a sort of a drop-on, drop-off section at the school. A lot of schools have those. And a lady parked her car at a very severe angle into the curb. And my granddaughter just walked up and looked at her and said, "Are you allowed to do that?" She didn't have an answer.
But
She did not have an answer. Yeah, it was very funny. Kids, they just, no filter. All right, let's move on to our first topic, and we're looking at the fastest stars in the galaxy, or are they too fast to look at? That's the question. Pretty quick.
Great question. So it's actually a topic close to my heart is this because when I was involved with the RAVE survey, the radial velocity experiment, which was a survey of star speeds and other data about stars carried out at Siding Spring Observatory on the UK Schmidt telescope, when I used to be astronomer in charge there. That survey, one of the things that we were doing was looking for high velocity stars that seemed to break the speed limits. And I think the fastest we found was about 400 kilometers per second, which is still a pretty impressive speed when you think of things like the Earth's movement, the Earth's revolution around the sun, which is a steady 30 kilometers per second. That's a pretty normal speed for celestial objects. But these things were going at 400. But since then, all that was a decade ago, and much more research has been done on this topic. And until a couple of weeks ago, there were only 10 stars that were known to be moving fast enough to exceed the galaxy's escape velocity.
Wow.
And they were essentially stars with velocities not that much different from the ones we were finding, 500, something like that. But some data that's come actually from the Gaia spacecraft, GAIA, which you and I have spoken about before. It's a spacecraft that measures positions of stars very, very accurately on the sky. And of course, if you do that, measure a position 1 year and then the same position a couple of years later, you can detect the motion of the star. And that's how these new record breakers have been found. So there's 6 more stars that are now known to be escaping our galaxy. And 2 of them are the record breakers. The runner-up in the galaxy escape velocity, the galaxy runaway star velocity
Olympics.
Yeah. What's the word again? The runner-up in the it's the that's right. It's the silver medalist.
That's right. Yeah.
Yeah.
I knew where you were going.
Yeah.
Yeah.
I couldn't get there. Too many other things going on. All right, the runner-up, the silver medalist in the runaway star record-breaking attempt is a star whose name I'll read in a minute. It's a bit boring, but that doesn't matter. But its velocity is a cool 1,694 kilometers per second.
Whoa.
Which is very fast. I could probably, I can't do it in my head, but I could quickly turn that into kilometers an hour. It's a lot. Multiply it by 3,600 and you'll get the answer. Now, that's the silver medalist, but the gold medalist in this competition, not that it is a competition, is a star that is moving at 2,285 kilometers per second.
Just over 6 million kilometers an hour, that first one.
Yeah.
What was the speed of the second one?
2,285 kilometers per second.
So that's 8.25 million kilometers an hour.
Oh, yeah, there you go.
Wow.
That's pretty good going. And the way I see, when I see a number like that, I think, wow, that is not far short of 1% of the speed of light. Now, that doesn't sound like much, 1% of the speed of light, 300,000 kilometers per second. But an object moving at that velocity, you will certainly see what we were just talking about a few minutes ago, relativistic effects. In other words, if we could see time going on planets around that star, we'd see the effects of time dilation, the time apparently slowing down at something moving at a high velocity.
Would they have planets if they're going that fast?
Well, that's a really good question. Because the next thing I was going to talk about, and it has bearing on your question there, is how did they get to these crazy velocities?
That was my other question.
And it might be that the mechanism that took them to to those crazy velocities would actually strip them of any planets if there were planets, because what is being conjectured about getting the stars to these crazy speeds is that what you have is a star that's been ejected from a binary system. In other words, a pair of stars, one of which is a white dwarf star, and white dwarfs we've talked about before. One of Rusty's favourite objects. These are stars at the end of their evolutionary life, and basically, if you add material to a white dwarf star, and sometimes they do leach material off a companion star if they've got one in orbit around it. When you do that, eventually you get to a point where the white dwarf doesn't like it anymore and explodes. In what we call a Type 1a supernova. And that is thought to be one of the possible scenarios in which you could blast out of a binary pair the companion star of one of these exploding white dwarfs. So this thing hairs off into the wide blue yonder at great velocity, and it may well leave its planets behind if they withstood the explosion anyway. So that's a really, really good question. There's some subtleties about the explosion sequence. There are various types of supernova explosion caused by these binary systems, and the one that's favoured, and I can't really talk about this in detail. But it's called a double detonation. The thing explodes twice, and so that is thought to be the thing that will give it energy sufficient to leave the galaxy at these extraordinary velocities.
That happens to me after I eat curry. If they
I don't wish to know that.
Dear. Just sort of a backup joke to that, but I won't say it. Yes, I will. Same colour too. We know their speeds, and they're travelling at a rate of knots, and it's quite an incredible speed. Are they going to exit the galaxy, or could they hit something in the process? Or is it likely that if they're approaching something, the gravitational effect will send them sort of in another direction?
Yeah, well, that's another great question. It's so. I mean, the bottom line is space is big, as Douglas Adams said, and there's a lot of space between the objects, so that the chances of them hitting something else are probably fairly low. But what may happen is the close encounter with another object, maybe a star, or possibly even a giant molecular cloud. These are huge aggregations of gas and dust where we think stars are being formed. All of those objects would have enough gravitational pull, probably not to capture the star because its velocity is just so high, but it might deflect it slightly. As it passes something massive, it may well be deflected slightly, so its angle, the direction in which it's traveling changes very slightly. Okay. But it's hard to imagine anything other than possibly a black hole having sufficient gravitational pull to capture it into orbit around it, or even to suck it in. So maybe these stars have got a long, long trek of a few millions, tens or hundreds of millions of years. As they leave our galaxy and head for another one, it may well be that they might, plunge into the center of that other galaxy, get swallowed up by the supermassive black hole at the middle. But I think that is such a low odds probability that you might as well just think of it going forever.
Yeah, wow.
That's probably what it'll do.
What is the required exit speed to get out of the galaxy?
That takes me back to the work I was talking about before. It depends where you are in the galaxy. At the radius of the sun, in other words, at our distance from the galactic center, which is somewhere in the region of 25,000 light years, it is roughly 400 kilometers per second, if I'm remembering correctly from the work that we did earlier. So some of those stars that we were seeing were, the ones that might just be squeezing out of leaving the galaxy, but they're nothing like the ones that we're talking about now.
Yeah. But they're still going to take a long time.
Yeah, let me just identify these objects. The silver medalist is J1235, and the gold medalist is J0927. These are quite short names for astronomers, aren't they?
And how far away are they? Do we know?
That's a good question. I don't have that that information in front of me, but I could check it out as a bit of homework there, because it will be interesting to know that.
Yeah.
I'll follow up on that. I can. It's actually a paper. Let me click on the paper itself. It is going to be published in Open Journal.
What it's called? Sorry.
Open Journal of Astrophysics.
Okay.
That's where it's going. And let me see whether I can give you a distance for them.
Okay.
Not easily, because they're the abstract of the paper does not contain that information. It does contain the velocities, though, and it does suggest that they're white dwarf.
Yeah. And a long way away. I suppose we could look it up on Wikipedia. They'd know. They'd have the answer. But yeah, those speeds are staggering, absolutely staggering. And there'd probably be a lot more out there, I imagine, Fred.
Yeah, that's right. Whenever you find things like this, you're usually seeing just the most easily accessible of a much larger population. And by easily accessible, I mean bright enough to be able to see with the Gaia spacecraft.
Very good. All right. And Fred mentioned the paper, but if you want to find out more, there's also a great article on Phys, Phys, phys.org. This is Space Nuts with Andrew Dunkley and Professor Fred.
0G, and I feel fine.
Space Nuts.
Yes, and speaking of very fast objects and ones that are very close to us, things in orbit. And a lot of those things are pieces of space junk, which are starting to become a huge, huge problem, are they not, Fred?
They are, yes. There's, we're faced with a number of issues when it comes to space junk. And I guess the biggest problem is the defunct satellites, the satellites that have done their job, they've run out of whatever propellants they need.
Yeah,
maybe the solar panels have got cracked or something like that, but they're at the end of their life. And there's about 2,500 of those, 2,200 or thereabouts, defunct satellites. Now, of course, there's another problem, and that is the smaller stuff. And there's well over 20, and it might even be more like 30 or 50,000 now, bits of debris which are tracked, stuff that's bigger than 100 millimeters across 4 inches. And then when you think about things that are smaller than that, which is not tracked, it's in the tens of millions.
Yeah, we're talking about everything from flecks of paint to tiny little pieces of
bits of screws and things of that sort. So what we're talking about here, though, is essentially an endeavor to try and at least alleviate part of that problem. And the part in particular that this company that I'm going to talk about is aiming for are the defunct satellites that are still intact. They're in orbit, but they're not doing anything anymore. And it may well be that the operator of those satellites want to deorbit them and make them safe so that they basically slow down, they come down through the atmosphere, burn up, and that's the end of the problem. They are contributing perhaps to some of the pollutants in the Earth's atmosphere, but that's a much smaller issue than the debris around our planet. And so you and I have spoken before about the various methods that organizations have suggested, both commercial and space agency organizations, to try and do this, involving, some of them involve grapnels, some of them involve nets where you shoot a net at something and then put a drag on it so it slows down. But this is a new...
harpoons?
Yeah, harpoons, that's right. That was another one. Yeah. This is a company, it's a Japanese company called Astroscale, who have, and in fact, they're funded partly by the UK and the European space agencies, so they've got significant resources that they're putting into this project. And what they've done, they've sort of devised a reusable robotic tug that will essentially deal with this problem. Their mantra is rendezvous, retrograde, burn, and repeat. So by that, they mean you find the spacecraft that you're, what they call the client spacecraft, the one that you want to bring down. you rendezvous with it, and then it's inspected. This little device that the robotic tug actually has a look around just to make sure the thing's intact and where can you hang on to it. And then by using a magnetic grapnel, they attach the spacecraft to it, the robotic tug spacecraft, fire the braking rockets on the tug, which slows them down, and then that injects the client spacecraft, the one they're trying to get rid of, into an orbit that will very quickly degrade because of atmospheric friction. They let go of it. That client spacecraft heads down to Earth, perhaps makes another 2 or 3 complete orbits before it finally burns up. But then they fire rocket motors on the tug to put it back into a safe orbit so it can go to its next client. And they call this...
wash, rinse and repeat.
Yeah, that's right.
Yeah.
That's the thing. Exactly. Rendezvous, retrograde, burn, and repeat. And it's the repeat that is the new aspect of this, because this little robotic tug has the wherewithal to do this several times. It's called ELSA. That's the name they've given to it, ELSA. ELSA, and it is an acronym for End of Life Service by Astroscale. Astroscale being the name of the company.
Gee, I wish they'd put the naming of these things out to tender, because I was going for Junkie McJunkface.
Well, that's right. Who could do better than that?
I know. I think that's great. Because you know where I got that from? It's because there was a tugboat in the UK. They did a public online thing to get a name for it, and someone suggested Boaty McBoatface, and it got 75% of the vote, and they didn't do it.
No,
I reckon it's awesome.
No, I think it's a pretty good one as well.
I like that.
Junkie McJunkface. Yes, I do quite like that.
Yeah.
So they've done a test flight already with a prototype model of this. This is Astroscale. Back in 2021, showed that it could do its repeated magnetic capture trick, and that then there was a pause by the company in its operations because there was some issue with the spacecraft, which they claim now to have fixed, and so they will actually be, I think it's next year, they've got another test flight, if I am remembering correctly. But they basically they say that their new spacecraft, what they're calling the Generation 2, with a docking plate, that's the thing that lets you grab onto the client satellite. They say it's got a lifespan of 15 years, which is really, quite a long time when you think of what this thing is trying to do. If it's pottering around, grabbing spacecraft, bringing them down, in response to the owners of those spacecraft requesting that, because you'd have to do that, or else it becomes an act of space terrorism if you grab somebody else's spacecraft and dump that when they don't want it. It's a very interesting prospect, and I think we might see more of this company. And more news about how the experiments are progressing, and it will be great to see it actually in service, if that is the case within the next couple of years.
Yeah. I suppose when it's at end of life, it will self.
Yeah, that's right.
Degrade.
Today, as part of the approval process for launching any satellite, you've got to have a strategy for the end of its life. And so today's satellites can actually, they can do it themselves. They can bring themselves into that orbit that will cause them to break up. And I think I'm right in saying that Starlink satellites, that's SpaceX's flagship internet provider system, they have an operational lifetime of 5 years, if I remember rightly, and then they will burn up in the atmosphere. And today that's mandated. You've got to show, before you get the ticket to launch, you've got to show that you can get rid of the spacecraft at the end of its life. But
so I guess we'll reach a time where all the ones that can't do that are dealt with, and then we've got a situation where it's going to be self-solving.
Yes.
But in the meantime, we at the moment have 7,702 active satellites in Earth orbit.
Correct.
And that changes almost every day.
Yeah.
But that's a massive number.
It is, and that actually includes the CubeSats. Because if you look at the bigger spacecraft, satellites that are more than 100 kilograms, it's about 5,000.
Yeah,
a little bit more than 5,000. So that, and most of those are Starlink, actually. Most of them are Starlink.
Yeah. When you consider that 60 years ago there were none, maybe one.
Exactly. Exactly. So you're absolutely right. I think, Astroscale's mission is really addressing those 2,200 defunct spacecraft that are in orbit, and that will, we hope, address that issue well, and perhaps make space a more safe and sustainable place.
So does that mean there's almost 10,000 of them up there that are in use and past their use by date?
Yeah,
that's right.
Yeah. These are the bigger objects. Yes.
Yeah.
Because it gets to, when you look at the smaller things, the numbers blow out. Hugely.
Okay, very good. Listen, I'd normally hold this for our question and answer episode, but because we've talked about this a few times lately, I thought I'd throw it in late in this segment. I don't have a name for this, but because we've talked about it, we've been asked for you to explain what a hybrid eclipse is. So maybe we can just tack that onto this little parcel of the program.
Yeah, okay. Delighted to. And indeed, I witnessed a hybrid eclipse a couple of months ago.
Yeah.
In off Western Australia. So think about an observer on Earth watching a total eclipse of the sun, and as we know, what happens is the moon's shadow passes over you, and what you see from the surface is the disk of the moon crossing over to completely obscure the sun. So the sun's completely obscured in a total eclipse of the sun, and it's by the sun I mean actually what we call the photosphere, the visible disk of the sun. We can then see the outer atmosphere, and that was beautifully shown in the April 20th eclipse. However, there is another type, and it comes about because both the Earth's orbit around the sun and the moon's orbit around the Earth, they're both ellipses, they're not circular. And so the distances between these objects vary slightly. And so there is another scenario where the moon is just a little bit too far away to fully cover the disk of the sun. And so what you get is what's called an annular eclipse, or a ring of fire eclipse, because you still see the disk of the sun, a ring of the disk of the sun surrounding the dark moon. So the moon's just too far away. Now, the hybrid one is effectively an annular eclipse at the start and end, but in the middle, where as the moon's shadow moves across the Earth, it's the curvature of the Earth itself that brings you slightly nearer to where the eclipse to the moon's disk. And so, what you actually see, if you're in the right part of the path of the eclipse, you will see a total eclipse of the sun. But if you're at each end of the moon's path of the moon's shadow on the planet, you will see an annular eclipse. And the reason why I'm struggling for words here is that I've just had a message coming up saying my battery's running out. So I'm just going to plug some power into it.
Well, that might explain why your face disappeared too.
Okay, yeah. So my face might come back. I'm going to close that. And
there he is.
Yeah. So I've now got power going to the phone. I should have thought of that. As you will gather, our listeners and watchers, we're in new territory here with a new trick.
Yeah, we had to find a workaround for a technical problem. So Fred's doing everything on his phone today. Okay, so there's all sorts of situations where what you're seeing of the eclipse can vary depending on where you are within the shadow, etc.
Yeah. So just to complete that, because I didn't explain that very clearly, in the April 20th eclipse, the path of the moon's shadow sort of started to cross the Earth over the Indian Ocean and wound up at the end of it off the coast of Indonesia. But in the middle, the curvature of the Earth brought you near enough that you would see a total eclipse. But if you were viewing at either end of the path of the moon's shadow, the path of totality, as we call it, then you would have seen an annular eclipse. And that's why it's a hybrid. It's two different kinds of eclipses in one. And there are, I think, if I remember rightly, let me think, I think it's 7 per century on average that you get. It's a small number.
Yes. Well, here we would have seen only 10%. Of
a
coverage.
partial eclipse.
But it was very cloudy, so I saw nothing anyway.
Yeah.
So I don't know who asked that, but there's the answer to your question as to what is a hybrid eclipse. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we will continue with questions, and we've got an audio question from Tim, who is actually part of the Bytes.com family, as he will explain at the end of this question.
Good day, Fred and Andrew. This is Tim Gibbs, the Friday host of Astronomy Daily. I was asked a couple of questions last week by a friend of mine, and I didn't know the answer, so I thought I would come to the font of all knowledge on Siding Springs. The first question was the Uppsala-Schmidt telescope at Siding Springs, which I think was used by Rob McNaught for a number of years in his NEO research. Is that telescope still at Siding Springs, and is it still used for anything? The second question was a friend asked, he had been told that the Earth has a second moon, Cruithne or Cruithnia, not sure of the pronunciation, and he wondered, is it really a moon, and are there others that people, the general public, do not know about? So, Fred, how many moons does the Earth have? Don't forget, folks, you can listen to Astronomy Daily with Steve Dunkley as the host on Mondays and myself, Tim Gibbs, as the host on Fridays. See you soon, guys. Thanks very much. Bye for now.
Thank you, Tim, and happy to give you a plug there. But and who's that Steve Dunkley guy they keep talking about?
I wondered that too.
Yes. All right.
Your brother?
He's definitely my brother. Yes.
Yeah, must be Steve Dunkley, the Dunkley brothers.
Yes. We could be a band. Well, Steve is a very, very accomplished musician, but I don't think I'd help him much in that regard. What was the first question he asked us?
It's about the Uppsala-Schmidt.
Yes, that's right, the telescope at Siding Spring.
So Tim is correct. It's a telescope called the Uppsala-Schmidt. That's because it was originally owned by the University of Uppsala in Sweden. And for a while, I think it was at Mount Stromlo, but came to Siding Spring Observatory. And by the way, it's not Siding Springs, it's Siding Spring.
Spring singular, yes.
Yeah. It came quite early in the history of the observatory. I can't remember when it actually arrived there. A Schmidt telescope is a wide-angle telescope originally designed for photography. It was modified in probably the 1990s to take an electronic camera, a CCD device, charge-coupled device, and was used very effectively, as Tim said, by Rob McNaught. Now, Rob was for many years the world's most notable asteroid hunter, looking for near-Earth asteroids. It was part of a program actually funded by NASA, administered by the ANU, to operate the Uppsala-Schmidt, and he was very, very successful in discovering many, many asteroids. And I'm always eternally grateful to him because one of those asteroids is called is it 5691? I can't remember the number, but it's called Fred Watson. So that's not one that is going to come near the Earth. In fact, it's a totally boring asteroid, which
it's going to disappear into obscurity.
It'll just continue wandering around in the main asteroid belt ad infinitum, and more or less as I do, really. So that's the story. But it's now some years ago, and in fact, I can probably date it because this happened round about the same time as the Wombalong fire, which almost took out Siding Spring Observatory back in 2013. 13th of January 2013, the Uppsala telescope was not affected by the fire, but that coincided with the time that the funding came to an end, and in fact, Rob retired. Not very willingly, I have to say, because he felt he still had much to contribute. But Rob still does great stuff. He's, I mean, retirement for Rob is probably just more of the same, but with a smaller telescope.
Yeah.
He's still doing great stuff. His Uppsala Schmidt, though, is no longer there. It has been removed. And if I am remembering correctly, it's being restored, I think, by the Tamworth Astronomical Society.
Okay. 5691, by the way, your asteroid.
Yeah, that's I thought it was. Yeah.
5691. Okay. Thanks, Tim, and we'll hear you on. Oh, he's got a second question.
The second question, yeah, it's Crunia. It's pronounced. It's I think it's spelled Cruinthe, I think,
right,
which is a Scottish Celtic name, Gaelic name, as we'd say. And it's an object which is not actually a moon of the Earth. It's in a peculiarly resonant orbit with the Earth. It sort of sounds, if you imagine your viewpoint of it from the Earth, it's a kind of kidney-shaped orbit going around the sun rather than around the Earth. So it's not a moon. But the reason why Tim has asked it along with Siding Spring is that that's where it was discovered. By another Schmidt telescope, the one that I used to be responsible for, the United Kingdom Schmidt telescope, still there, not operating at the moment, but still in an operational condition at Siding Spring, now in fact owned by the ANU. But that discovery was made by a duty observer on our staff. He was there for quite a number of years. His name's Duncan Waldron. Duncan might actually be a Space Nuts listener. Because he looks after the Brisbane Planetarium up there north of the border. So if you're listening to this, Duncan, hello, and I hope I'm telling the truth here. He was the person who discovered this object in an asteroid discovery program. Essentially what we did was, with the UK Schmidt telescope, we were taking survey plates, we were surveying this whole sky, taking these 6-degree square photographic plates, showing the stars and other objects, and of course in doing that we picked up asteroids and comets, and Crunia was one of the asteroids that was discovered by Duncan Waldron with the UK Schmidt telescope at Siding Spring Observatory. So thanks for that, Tim. All good stuff.
Yeah, very good, Tim, and we'll catch you on the next episode of Astronomy Daily. Just as a matter of interest, though, you and Tim would be keen on this. The Pan-STARRS telescope in Hawaii has discovered another asteroid that is orbiting Earth at the moment, 2023 FW13. FW, Fred Watson.
That's the one. Yeah, which is temporary, though. I think.
Yes, that one is.
I think that's the thing. There's no permanent second moon of the Earth.
No, not at all. All right, thank you, Tim. Let's move on to a text question from Jeremy. Please, can you give us an update on the Great Attractor and if the James Webb Telescope will be able to see it more clearly as it's on the far side of the Milky Way galaxy, making it hard to see?
Yeah, so great question again. The Great Attractor is something that was postulated back in the 80s, I think, if I remember rightly, to explain the motions of galaxies in space. When we look into space, we see lots of galaxies, obviously, but as you know, they're all receding from us because of the expansion of the universe. That's called the Hubble flow. The flow of galaxies away from us. The velocities are higher the further away you look. But superimposed on that are what we call peculiar motions. The individual motion of a galaxy itself caused by the gravity of other objects around it. And the way to imagine this is we often use this analog. If you think of a river flowing and then boats on a river, the boats are moving around on the river, but they're all being carried along by the flow itself, the flow of the river. So they've got their individual velocities, but that's superimposed on the velocity of the flow of the river. And it's the same with the universe. What we call the Hubble flow is the flow of objects due to the expansion. But galaxies have their own motions, peculiar velocities, which are caused by gravitational attraction. And so back in I think, as I said, it was the 80s, the astronomers of the day found that a lot of galaxies seem to be being pulled towards a point which is behind the disk of our galaxy, or it's sort of in the same direction as our galactic disk. And that's a region we call the zone of avoidance. And that's an old term that goes back to when we didn't know what galaxies were, because astronomers could see that there weren't any of these weird spiral objects in that region. And we now know that that's because the Milky Way's disk is dusty and you can't see through it with visible light telescopes. But you can with infrared telescopes, which is why this is a great question that we may well be able to use the James Webb to look more deeply into that region of the Milky Way, which we think hides the Great Attractor. Now, the latest work on the Great Attractor identifies it with a cluster of galaxies, I think in the constellation of Vela, if I remember rightly. And it's thought that it's not as big an object or as big a gravitational congregation, if I can put it that way, as we used to. We think that motion of objects towards it is partly due to other clusters of galaxies which we can see. So there is ongoing work on the Great Attractor, and no doubt when the James Webb Telescope finally points at it, and that might have already happened, there may be papers in progress that we haven't seen yet. But I'm sure we will discover more about the Great Attractor from the Webb Telescope.
Yeah, I hope so. That'd be exciting. Of course, it comes down to who wants to do what and booking time and all that sort of thing. It's like trying to get a car park at Sydney Airport, really. Sometimes.
That's right. You've got to book it in advance.
Yes, you have. Thanks, Jeremy. I know there was a lot more to your question, but we just stuck with the Great Attractor section of it for today. And David has a question. There are zero assumptions in my question. It may be a good question. It may be a logical question, but simplistic with known answers, and I'm simply not educated in the field. Say we observe light from a galaxy 10 billion years away. Are there not numerous disparate past factors no longer active now over the 10 billion light years of travel to us that have affected the light spectrum we perceive now? If, say, 9 billion years ago, anything, the expansion rate of space, the various gases of another galaxy that is no longer there, etc., caused a shift in the spectrum of light from said galaxy, and that causative factor was no longer active, would the light we perceive now not still carry that past spectrum shift message, despite the fact that the cause of said shift is no longer affecting the light? Love that question.
It's got a simple answer too.
No,
it's yes.
That's yes. Yes.
So David's quite right, and there are examples, there are many things that can affect the light when you've got such long light travel times of billions of years. One of the commonest things is that perhaps the light may have passed close to a cluster of galaxies, which will have deflected it and caused a gravitational lens. And even if that cluster of galaxies isn't there anymore, and it probably is, but even if it wasn't, the light coming to us would still come from the direction that it looked as though it was coming from because of the gravitational lens and be affected in that way.
Yeah.
So yes, light, in a sense, any photon of light that comes to us from deep space bears the scars of whatever it's passed through. And the most fundamental part of that is the expansion of the universe. So its wavelength is stretched by the expansion of the universe. But other phenomena like passage through gas clouds and things of that sort, yes, it imprints information on the light, which is still there, even if the object itself might not be or have moved along somewhere else. So that's fascinating.
Yeah. So that's intriguing because it does mean that you're not just learning about the source of the light, you're learning about what's happened in between the emission of the light and us receiving it. That's really interesting.
And that's why, it applies to radio waves as well. That's why it's such an important diagnostic of what's going on in the universe to the fact that that light does carry with it a record of not only where it came from, but where it passed through on the way as well.
Yeah, amazing. Thank you, David. That's a really insightful question and well asked. That's it for us in terms of questions. today, excuse me. But if you do have questions for us, please do send them in via our website, spacenutspodcast.com. Spacenuts.io is the other URL. You can use either. If you put them together, you see us twice. But you can send us text and audio questions on our homepage. There's a link on the right, or the AMA tab is where you can send questions. Just as long as you've got a device with a microphone, we can take your recorded questions. Of course, as I always say, don't forget to tell us who you are and where you're from. We love to know that. A couple of those questions came from YouTube, so that's probably why we didn't pick up the names. But it's great to have YouTubers starting to get more involved. And we want people from LinkedIn to get involved as well, because we'd like to be able to do live casting via LinkedIn, but we need 150 followers to do that. So if you'd like to follow Bytes.com on LinkedIn and join us there, we'll be able to do live output as we record, which is what we're doing today, although I'm not feeling very live after all that. But it's a simple case of going to LinkedIn and just do a search for Bytes.com, BITESZ.com. And if you follow us there, we'll be able to grow our podcast via LinkedIn as well. That brings us to the end of another episode. Fred, thank you so much. And thanks for working your way around our technological glitches today. We've been having a lot of those.
Yeah, but we seem to survive. Hopefully that will continue. Thanks again, Andrew. Always good to talk, and speak soon.
We will indeed. Professor Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks to Hugh in the studio, who didn't turn up and didn't do anything today. But how is that different? And from me, Andrew Dunkley, thanks for your company. We'll see you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.